Here, I am Efraim Grynberg, Senior Director of Global Sales Engineer, and I'll talk about our customers. And again, we are talking about WEKA, the data platform for AI. And again, what I want to talk today is about some of our customers, okay, and use cases. And before I go to that, I want to tell something that is happening to me lately a lot, which is people asking me why I like working at WEKA, and for good reasons, right? People that are very interested in us. And my answer have three parts. The two parts are easy, right? Are the ones that when I was looking to join a company, I was looking for great technology with great product and great vision, and also a leadership team that has that vision and wants to do new things. The third one, I was not thinking about that when I joined WEKA, and actually it's one of the ones that I enjoy more, and it's our customers, okay? Our customers, we are enabling our customers to do things that they didn't think that they could do or they wanted to do, but they didn't know how because all these data mobility problems, scalability problems, and things like that. Now, our customers are pushing the envelope in any field they are doing. And I, in my work, have the privilege to get these mini dissertations of the top engineers, top data scientists, top scientists in general, about how they are looking at solving new problems. And this is a little bit what I wanted to bring. I choose three use cases, okay, or three customers. And the reasons I choose these ones is because these are, of course, AI use cases. And these are use cases that are in production today. These are use cases that are bringing business values, business impact outcomes to customers today. This is not a research mode that maybe will do something in 5 years. This is something that is happening today. Okay, the first one is about intelligent manufacturing. Manufacturing sounds boring in general, but actually it could be very, very interesting, mainly when you have complex processes in manufacturing, okay? And the one that I want to bring is about LCDs, how people is manufacturing LCD. Again, this is a real project that we have in production today. Now, before we go to WEKA and how we solve all these things, let me tell a little bit about how these things work. If you know an LCD, if you look at an LCD, it has several layers, right? And there is a pixel layer, a backlight layer, another layers that I don't remember, but it also have a glass layer. The glass layer is like considered the bottom, okay? But it's actually what we touch when we have an LCD, okay? And this process actually has a lot of similarities, like the idea of getting this layer of the glass layer. It has very similarities with wafers, okay, with chip manufacturing. So first of all, there is the concept of a mother glass. In the newest generation, a mother glass is the size of 9 feet by 9 feet, okay? And the LCD screens are cut from this mother glass. Now, this mother glass has to be super clean. There is very clean environments, so actually clean rooms, as in the same as when you are producing chips. Okay, and these machines are extremely expensive. So actually building a manufacturing plant for these LCDs are extremely expensive, billions of dollars. Yield is extremely important, okay? Maximizing the cost of all this investment, predictability for supply chain, and making sure that you actually respect the contracts and you serve your customers in time. And another thing, the materials that you use to produce these different layers is extremely expensive. You want to reduce as much waste as you do. What companies are doing today, and by the way, with WEKA, okay, the traditional kind of manufacturing, there is a lot of visual inspection, again, as you have in chip manufacturing. So what we are doing right now, or what customers have been doing and they are continue doing because it's important, they are with GPU servers visually inspecting the glass for any defects, okay, before and after the cutting. So we are talking about 1.7 million in this case, from this customer that is a huge manufacturing plant, 1.7 million pictures per hour that need to be visualized, inspect at the same time, okay, for every pixel. A lot of QA, analytics, quality assurance, everything needs to be, before they cut the glass, they need to check that there are no defects. And after they cut the glass, they also need to check that there were no induced defects. So visual inspection and processing data constantly. But this doesn't have anything to do with AI, even if they are using GPU workloads to do that. By the way, one of the things that they want to do, which is interesting for me at least, is that if they see any defects, they will reposition the angle of the glass or of the cutting machine to make sure that they take advantage of most of all the remaining glass they can do. Now, the problem is that if there is a defect, okay, in the processing or an induced defect on the glass, they discover this after the fact, either on the terminated product or on one of the inspections, and it could take hours and days until they really understand there is a problem. And there's a lot of waste on time that they wasted, actually. So how can we help, or how this company is trying to say, let's predict if there is a defect. Each one of these machines that we are talking about, okay, have a lot of sensors. And each sensor is different than the other one. Like we have power sensor, vibration, temperature, movement sensors is mechanics, okay? This is all data that it is being used to say, okay, there is an alert, I have a power problem, I have a moving me problem. But again, this is done only when this is discovered only when the problem happens. This one of these sensors is taking a sample every millisecond. It's a huge amount of data. Now, what if we can get all that data in advance, okay, or collect all that data, create an AI model that actually analyzes if there is anomalies or changes in trends. And then we can predict that actually there is a machine that it will induce a defect in the glass before it happened, even 2 weeks before. I can go replace the part and nothing happened. So we start understanding that the machine or part of the machine will fail before it really fails or before it induces a defect. And that saves a huge amount of money. What this company is doing is actually that, okay? And what is in, but the difficulty with that is how do you analyze, okay, about 1 petabyte? You mentioned who is going to move 1 petabytes of data. They have between images and the different sensors about 1 petabyte of data per hour to process. Okay, they need to ingest all the data, okay, into some type of central repository, hopefully, and not hopefully, but this WEKA Data Platform. Okay, they need to, in real time, ingest the data, transform the data, analyze the data, and then expose that data to a dashboard to understand if there is any anomaly.
Did I hear correctly? You said 1 petabyte data per hour?
Yeah, between images, sensor data, and everything. It's about, I did the math, it's about 300 gigabytes per second. But this is not only the interesting thing, right? These sensors produce different type of data. Everyone a different type of file. They expose the data, they ingest data through S3 that goes directly into WEKA. It's transformed online, okay? Then it's processed, analyzed again in real time, and moved to the dashboard. Each one of these cycles, okay, happen every 15 minutes. Every 15 minutes, we are refreshing the dashboard. And at the time that we are analyzing data, we are transforming new data and ingesting data. So all these processes happen continually. Now, you say, okay, we need a lot of flash. We need a lot of CPU cores. But the reality that is that for this company, being able to process the data and know that a problem will happen before it really happens saves huge amount of money. The business outcome is clear, is tangible for this company. And this
so
is
a question on the on this cycle that you're doing, because the previous discussion of the pipeline was that there's a lot of stages to it, lots of data copying and so on going on, which seems more batch oriented rather than full stream processing. So in this example, are they actually doing all those load store cycles to the storage, or are they using a more inline, like real-time stream processing?
They are using real-time stream processing, but
okay.
But again, the interesting part, at least for me, from looking at this from the IO perspective, this inline stream processing is happen as you are transforming also on the same kind of data repository, data platform, and you are analyzing and exposing. It doesn't move from place to place. If you think to imagine that before WEKA, every time they would need to move the data to a different.
So Efraim, it's really the training has done earlier, and this is more or less inferencing in real time on the manufacturing line to try to ascertain whether a blank has defects or not.
I agree. Well, but actually,
it may not be inferencing, right? Because some of the data you may not be able to immediately consume, right? The hope would be that eventually you could get to that sort of real-time inference, but some of that may be just data you're capturing in the hopes of later analyzing it.
I'm assuming all this data was used to train the QA agent to ascertain whether a defect is present or not.
Eventually.
Eventually.
So there is a model that is in place, but actually they are getting data, I think, new data from the last, I think, 20 days, all the time constantly, and retraining the model, retraining the model, retraining the model.
I understand all that.
So,
okay, I'm good.
So there is another part of retraining the model all the time with new data, because things change environmentally in the clean room, right? This is going to happen. And again, this is something that is in production today, which is very, very, for me, impressive. By the way, again, all the idea of the pipeline, and you can think about this pipeline not being one stacking behind the other, right? Like several of these pipelines on the same data platform. Okay, let's move to another use case. And this is a use case that I can talk about the customer that we are doing. Actually, all the credit goes to these guys, Atomwise, that if you don't know about them, you should read because they are extremely interesting. Okay, what Atomwise is doing, Atomwise is a small, I don't know if they are any small not right now, but they are a startup. I think they are in Series B right now. They kind of got $130 million, but don't take it, maybe those facts are a little bit incorrect, but they got good Series B. And what they are doing is applying AI models to accelerate drug discovery. And what you are seeing in the screen here is a 3D modeling of a protein of the coronavirus that we are all dealing with yet. And the idea is that the approach that Atomwise is doing is actually, they are using a training model, a network that actually is very similar to computer vision. So instead of saying, okay, let's try to recognize pixels into edges and edges into features of the face, for example, and those features into faces, okay? They are applying deep learning in 3D modeling of the proteins. So they create a protein, they try to understand, okay, the relations between the atoms. Those relationships will tell them things about the bindings, that the binding affinity that they can, because the idea is when you create a drug, and I am not a scientist, is that you want to create a molecule that can bind to a protein and then do things to that protein, okay, to destroy and actually avoid the cure, avoid use. So this process today of binding affinity, when you are trying to start, is a very iterative process that is kind of analogical. Scientists do it in labs, and it might take years, months, days, every iteration. So they are actually doing the 3D modeling of a protein and trying to understand what is the binding that actually will work better for the molecule that they want to produce as a drug. Okay, and they are, again, using very similar models to what they do with image recognition. Now, the interesting story about a little bit more of data points, each one of these proteins models, okay, or for each one of the experiments, sorry, they have about 4,000 protein targets, okay? Each one of the viruses might have different protein targets. And they, for each one of the models, they are actually collecting 15 million experimental measurements, or it's not experimental measurements because it's modeling, but the equivalent. And this is represented everything by very, very small files. These are not images. They are very, very small files, vectors, things. The interesting part is that when we started to talk with them, actually, there was Timon talked about AI process that is mature. So Atomwise started as a very small kind of startup that they were training data sets that fit in one server. But they started to grow, they increased the data sets, they have more projects, okay? They decided that they need a distributed compute, okay, cluster and file system. Things were not fitting on one single GPU server or GPUs. So they started to look at different things. Now, they tried several iterations and all the moving, like even if it is not very high in volume, the amount of files moving from one place to another was extremely difficult for them to produce. It caused a huge headaches. They have a lot of DevOps in AWS. By the way, all this is running in AWS. What they are trying to do now is create supercomputings in AWS for limited amount of times, okay? And they are actually spinning thousands and thousands of spot instances of GPUs, okay, to connect to a relatively small WEKA cluster, okay? And actually, and you can here go into the webinar where we are jointly presenting, they reduce, because all those hurdle of moving data, creating those instances, all that stuff that they needed to do, okay, it was taking each project about 3 months. When they started to create this model with WEKA, okay, they reduced all that project to a single week. And it's of course about how much fast you can train your model, but it's also how effectively you can manage your data cycle, okay, to be able to actually reduce the project of the time. Now, you can see the YouTube video there. You have the Atomwise guy saying, and I am stealing his phrase, like they needed to rethink all of a sudden how they are doing their business, because all of a sudden what took 3 months was compressed to 1 week. The amount of work they could do was significantly larger. And again, the previous use case was on-prem, right? Fully, this is on the cloud. You can take WEKA, run your projects, whatever you want. Questions?
So with both this example and your example of finding defects in glass, you've kind of given us like an aggregate of how fast it has been improved. But you haven't really walked through the various different steps in the pipeline to explain, you know, how the various different steps were improved. So I mean, you're telling us it's 92% improvement over what had been, but you haven't really walked us through the process. The description of what you've done, what they are doing in both the glass and the this, you know, genome or cell processing here, very good descriptions of that, but you haven't actually explained to us how WEKA is actually helping this process along, other than just giving us an aggregate, like it's better this way.
Yes, no problem. So actually what they did here is a little bit different than the typical pipeline, but you can say, first of all, they need to create all those 3D modelings. Okay, so there is a lot of compute actually to create the data. Here, there is no the idea of ingesting data, but there is the idea of creating all the data set each time they have a new protein or a new virus to do. So here it's not so much about ingesting, it's creating. It's a very intensive computational process. But now they want probably to train this based on these models several times. What they are doing actually is taking a snapshot of the file system, okay? They upload that snapshot to the object store or the tier that they talk about, okay? And now they are saving that as a different project. Now they say that they want several, for different projects, for different experiments, several copies of this, okay, of these proteins or models, and they want different kind of algorithms to try on them. They actually can, what they can do is to spin up a different copy of this snapshot, a different file system, okay, and attach to that many GPUs, okay? So actually now they can parallelize the work, because from one snapshot that you have of that data set, you can parallelize the amount of work that it's doing. So it's a little bit different than the pipeline, but it's exactly other of the features that the data platform allows you to do. You don't have to copy the data all the same. It's just a snapshot that you create.
Okay, and what you just explained makes an awful lot of sense. It had not been clear until you just explained it that way. So
perfect. Thank you for the
it's
yes, another good things that also it's all containerized what they are doing, the way they are working to spin all these things. And we are integrated with AWS EKS directly, and they use the managed services of AWS. That's another part that actually saved them time and management hurdle for a company that they want to do science and not IT or DevOps, right? And the other one, we have 12 minutes, so I will go by this very fast because I want to leave time for Q&A. But autonomous driving cars, that's the holy grail of AI today, right? We have several customers that are doing AI ML or autonomous driving. Actually, we are not only customers that are doing autonomous driving vehicles, we have vehicles, trucks, and even a company that is doing autonomous driving airplanes. Okay, features, everything training. Now, there are two ways to do training or to create models for autonomous vehicles. One is the LiDAR and the other is the image. And what I want to talk is about images and the problem of scale with images. Now, in one of our customers, Too Simple, by the way, is one of our reference customers that I can name. They are doing trucks, and actually they are using also cameras, not so much LiDAR sensors. One of our customers also are using cameras. And imagine, just to understand the scale, one car that has 8 cameras, okay? And each camera is producing 20 frames per second. Those frames are not super high in quality. You don't need a lot of clarity to understand this is a tree. I don't want to go into that tree, okay? But if you say 8 cameras, 20 frames, 1 hour, that is producing above 500,000 of frames per hour, one car. Now you need many, the scale is massive, which means, and my point is here, is that for these companies where actually the autonomous driving part is the main business, they want to collect as much data as they can, as much data as they can. They start small, they start to grow, they want to be able to add more compute, and this is all about scaling. So you want to scale not only on compute, you want to scale on capacity, but then you need linear scaling of performance. Now, in trainings, you are doing a lot of lookups. We saw, even in ImageNet, we have very small files. Now, metadata operation is extremely, extremely important. You cannot size your cluster for something that works with, I don't know, billion images. If you don't have a system that can scale on all the performance dimensions, throughput and metadata and IOPS, as your data scaled, you're going to burn your metadata servers. You want something that can scale continuously. When we started with one of the companies 4 years ago, okay, their data set was a few petabytes. Today, we have tens of petabytes all on flash with things that they are training. And they are training on all the data set, which means that they are producing more and more and more metadata operations. We see in this cluster throughputs about 1 petabyte per second, okay? 1 petabyte per second, and millions, tens of millions of metadata operations at the same time. So again, I am doing this in a very, very small compressed time because of the time, but the idea is that you need to have a system that scales as you grow and mature as a company, and your data sets become bigger and your training models need to be more accurate.
For your target customers, the people you're marketing to, like I'm assuming you're not marketing to people who have an AI workload that they run every month and it's only a side of a core system. And maybe they're like the typical one I always hear about, like retailers who are doing sentiment analysis and they're only doing it like every week or every month, and it's not really that workload intensive. So they're probably just going to use whatever systems they already have. But can you describe for us sort of, you know, who's going to find the cost benefit and risk analysis of your solution just such a great thing? They want to marry your solution. They want to celebrate birthdays with it. You know, who is your target, you know, your core type of organization or people that you're thinking this is the solution for?
So first of all, we tend to work with companies that they are already in a relatively mature state in terms of AI. The people that they are starting with AI, they are doing all in their computers. But actually, the guys at Atomwise, when I started to work with them, they have 5 million in funding. They were very small, but their business is based on AI modeling. They understood that they will have that scaling problem very, very soon. So with them, actually, we started with in a very early stage, but they being a company that all their business modeling based on AI, for them was easy to understand that we need. For other companies, it goes into a mature stage when scale is a problem. Okay, if you are only exploring and starting, you can use WEKA on AWS with very small things. Probably you won't want to have a full on-prem installation. Even though what we see is that companies that are starting to explore AI, they have huge amount of data, any case. And generally, we can speak with them not only about AI, so AI come after, but if you have a huge amount of data and you are in the HPDA, you need analytics, WEKA is a good target as well. Last week, I was talking with a company that actually we are helping them on EDA workloads. No AI, EDA. Again, but they are now starting to explore how they can apply AI on EDA because their capacity and the amount of data that they have is exploding, how they can make it efficient. So again, those companies that already have huge amount of data, they still are a good target for WEKA. And
because I saw the problem statement that you went through, the pipeline of everything, of copying data and everything. Like anyone doing any type of analytics has already compressed that and has stopped moving data around from, ingest and all that other. So yeah, I think you have a great story for anyone who's using that sort of problematic, costly way. And a lot of times they might have an analytic process and they're just now starting to add ML, let's say, to help do that, either transformations or the other enrichment that they do to data. So I could see it both as an AI solution and just analytics in general.
Yes, it's one of our great targets. HPC actually talked about that pipeline actually is something that we repeatedly see in many use cases, or at least in the 4 to 6 big use cases that we focused on. They actually are very similar in that. But we are talking about AI today, so we focus.
Yeah, no, that's good. Because I find that the companies that do this move, Ray, 5 times, is not because they intentionally designed that way, but because their tools were in different systems and even different server racks, and they were moving the data rather than solving the pipeline problem. And I think a lot of what I've heard today is about solving the pipeline challenges, and that almost all the bad designs happened because no one was funded to make it efficient until it got to be too expensive. And no one cared about performance, they cared about expense. And then they came through and said, I need to optimize both performance and my cost. Yeah.
Thank you. You described that beautiful.
So early on, you talked about near edge kinds of solutions is something that was coming up. How do you deploy something like WEKA in a near edge environment?
Okay, so, yeah, great question. So it depends how the edge is, if you need to ingest data or just read data. But one of the things that you can do is we can work in an hybrid model. Okay, you can have a big, huge kind of WEKA deployment in a centralized model, on-prem or on the cloud. And then you can have smaller deployments of WEKA, okay, on the edges.
So now about replication from spoke to spoke kind of thing, is that?
So through our snapshots, exactly, you can actually move data incrementally from one place to the other, okay, and repeating that data. That's actually
you have like a mini WEKA cluster in the edge and a central repository with a lot bigger storage.
And that data is, again, could be from edge to centralized or from centralized to the edge, depending on what you need.
And you also mentioned SAP, SAS, Oracle, and those sorts of things. How do they plug into a WEKA solution?
Yes, so there is a lot of exploratory use cases that we are using. Actually, Shimon is working now on a solution for SAS. I will let him answer better about that.
Even though SAS is already out there, it's not even future, it's done. We did the work, we proved the numbers. We worked, actually, again, this is AI, but you mentioned SAS. So SAS is already in multiple markets that we're already in, financials, life sciences, even and more. We actually ran through the workload of running SAS, running the IO loaders, that what they consider as complicated workloads for SAS. We showed amazing value, because when you look at the performance characteristics of what we're doing, so first of all, in terms of performance, SAS has this notion of how many megabytes per CPU core that is running the SAS analytics. They require 150 megabytes per core. On a single SAS client, we showed 500, which is amazing, because eventually you run your SAS analytics four times faster, right? Also, we show the scalability, because when we talk about WEKA, it's about, we like to talk about performance, but it's not only performance, it's also about scalability. How can we scale the cluster so that you get massive capacity on that same performance? How can we even send the SAS data to the cloud and run SAS on the cloud? So it's already out there. We actually work with our partners at HP on producing that content, and we can share it with you. So it's already in the present. It's not good.
You had a screen about too simple there, 7x improvement about performance compared to NFS. And then you highlighted NVMe. Could I just ask, maybe it's a little too into the weeds, but that type of NVMe, was it traditional NAND, or did you find any value going Optane, say, or
no, just
that's what I was
normal TLC NVMEs you can buy from many vendors, nothing special there.